Hey, it's Steve. It is May 5th, 2017. Time is 16:51. It is 49 degrees Fahrenheit out, and as you can see, it's sunny for once again. But this is an introduction to a Geo Ramp. I actually recorded most of it earlier today because even I won't risk this while driving. But remember in the last episode I talked about a special geology protractor we use? This is it, okay? And you can see it doesn't look like the ordinary D school protractor you used to use. Those things are inaccurate as hell. But this allows you to draw very accurate angles and diagrams to within, using straight lines, to within about half a degree depending on your scale. But this one's in inches. The bottom scale's tenths of an inch, top scale's 20ths of an inch. This is your degrees. You see 90 at top, and then it goes down, and it goes down to 0. But basically, how this works basically is you draw a line, and then whatever angle you want. Actually, I'll flip this over. You're gonna see this again in the next Geo episode. Whatever angle you want, say that's your horizontal. You just rotate it till you get your degrees here that you're looking for. Then you draw your line, and that's how I made the. That's how I made this diagram. This was from the last episode down here. But I'm gonna actually, following this, I'm gonna actually show you how to do that. I actually did draw one for you to show you how to properly use it. And then I did a check on it to see if my result was accurate. And anyway, well, I'm gonna get into it now, and I hope you will learn something. Okay, so let's get into it. You can see right here, this is an outcrop description, like I was on the road cut, and I described it accurately. The road dips about 4 degrees. I have my measurements, my units listed at top. That stuff that says like north 10 west, 40 northeast, those are strikes and dip measurements. And my goal here, as you can see in the upper right hand corner, is to derive a local thickness of unit 2, which in this case is a sandstone. I made up some descriptions here for standard, standard units of the area, and as they're defined, and that's going to come in key to where I put my boundary for the sandstone at the upper contact. Okay, so this is how you use that protractor I just showed you. You want to make your line to the horizontal, and I know I have a 3-degree road dip, and I already went over this, so I'm not going to show you here how to go over it, but that's your center. That's where you'll make your degree measurements, angles from. Okay, so you put that down on the paper, and like I said, you have a 4-degree dip, so you find your 4 degrees to make your horizontal line, which is what I'm doing here. Okay. So I've made my horizontal, and that's the upper contact with my unit 1, and there's my lower contact unit 2, and I actually have a strike and dip on that. Now that's my unit 3, and I have, you see that's a kind of silty there. It doesn't fall into the general description, but I do have a definition for the unit at a local scale, and for unit 3, which puts lower contact at the first solid limestone bed. So that's where I drew my contact. So it is defined in this case. Okay, so I have a strike and dip. It's actually on the bottom here, but first I got to draw my line to see my apparent thickness. And there's the lowest limestone bed, so I'm going to draw a line there. Okay, and I have 1 inch is equal to 10 feet. I always draw bar scales. I don't just write 1 inch equals 10 feet in case somebody needs to copy it and they don't copy it at the same scale. Okay, so I measure that line, the horizontal, for apparent thickness, and I get 36. Or I get 3.6, which would be 36 feet. So 3.6 inches, which at this scale is equal to 36 feet, and I'm going to draw everything to scale, because otherwise it'll mess with my angles. if I give any vertical exaggeration or try to shrink my cross section. So I already drew the horizontal line for what I'm going to do for the graph here. Okay. So I can start on the lower contact anywhere, it doesn't matter. I draw a line. Okay. And I measure out 36 feet, which is 3.6 inches in this case. Okay, draw a 90-degree line from the horizontal, just so I know I have my 36. Now I'm going to do the angles, and this is where that strike and dip comes into play. I'm just going to use the dips here, but there's my 36 feet, and I have a dip, actual dip at the lower contact, which is 40 feet, or which is 40 degrees, sorry. Strike isn't going to really matter that much here. See, we have 40 degrees. My strike is north 10 west. A lot of times you have a parent dip. This isn't applicable here because we're going to draw both lines, just happen to be, both dips just happen to be exactly perpendicular strike in both cases. So this is going to be a 40-degree angle. I'm going to extend the line to make sure I can get my thickness. Okay. Now, at the upper contact, I do not have an exact measurement, but I have one really close, like within a foot. And in this case, it just happens to be exactly the same as at the bottom of the formation. So I'm just going to do exactly what I did before, except at the other end, I'm going to draw a 40-degree angle from the horizontal. All right. Okay, so there's my 40 degrees. And like I said, I'm just going to write my strike there. It's not applicable here because they are in a straight line. They are, so there's no apparent dip here. If there was, you'd have to do more complicated graphical representations, one in a plan view, one with the cross section, and so on. But here it's not necessary. So now what I'm going to do is measure my thickness directly, because my thickness is going to be where I just wrote that unit 2. It's going to be in between those two 40-degree angles. It doesn't really matter where I measure it here, as long as it's, see, it doesn't really matter as long as I draw it perpendicular to those other 40-degree angles and I get one right triangle. And the only reason why I need the right triangle is to confirm this. Now there I have another right triangle to show you that they're perpendicular to one another. So I measure my thickness and I get a thickness of unit 2 as 23 feet. That's my actual thickness of that unit. Okay, the 36 feet was an apparent thickness along a transit, but the actual thickness graphically is represented as 23 feet. So how do I know this is correct? Well, I'm going to do a check. And just another look at the protractor. Okay, well, how do I know that that 23-foot thickness is correct? Well, I'm going to show you here. I already redrew basically what I did on the last one. 1 inch is still 10 feet. There's my horizontal, 36 feet still. Alright. And I needed to make a right triangle, so I had to make sure I was butted up right against the horizontal there to get my hypotenuse. And there's my 23 feet. Now in this case, that makes this roughly 28 feet, and I have my 40-degree angle, but I also have a 50-degree angle due to the that 23-foot thickness. Okay. So there's that. That makes that 40 degrees. The other one sticking out, the unit as before, is still 40. Alright. But this angle over here is 50. So I directly measured that. Okay. Now, I didn't need that angle. I just showed you to show that if you add those three angles up, 90, 50, and 40, you're going to get the 180 degrees. So that's one check, but you really need the Pythagorean Theorem to do this, which is right here. So I have my a squared plus b squared equals c squared. My a squared, in this case, I'm using 28 because it's one of the legs. My b squared is 23, the other leg. And my hypotenuse is 36, and if you square 36, you get 1296. Okay. Now, I square 28, I get 784. I square 23, I get 529. But that equals 1319, which is not equal to 36 squared. 36 squared is 1296. But this is a graphical representation. So I subtract the 1319 from the, I subtract the 1296 from the 1319, I get it 23. My margin of error for the lower value is only 1.8%. Okay, so I'm really close. It's less than 2%. So for all practical purposes, is 23 feet correct thickness for that, for unit 2 that I did originally for my line of transit? Yes. It is. Okay. So that's the Geo Rant for today, and I hope you learned something. Oh, wait. Before I do that, I forgot I did this. But I actually did solve it through trigonometry, and that's the circle values are the ones that they actually are. And as you can see, in order to get that actual 23-foot thickness, so, yeah, those are the actual numbers. You can see they're really close. But anyway, now I'm done. So I hope you learned something.